Okay, maybe we can start. So I've talked about pool-tight families and the fact that one can always choose a minimizing sequence that is pool-tight. So in particular, every varifold in the critical set is going to be stationary, but stationary is not enough. So the key notion in the proof of regularity is the notion of almost minimizing varifold. So let me do the definition here. You say that a varifold V in Vn of m is Z2 almost minimizing. In some open set U, its definition, if for every epsilon positive, I can find some delta positive and some chain T that belongs to Zn m n minus u Z2. And by that I mean that the support of the boundary of T is contained in m minus u. This is a local thing, such that if I look at the varifold distance in U between V and the varifold induced by T, this is less than epsilon. And I have the property that for every deformation say T tilde into the space of cycles, let's say with boundary outside U, a family that is continuous in the flat topology with the properties that T tilde of 0 is equal to T, the support of T tilde of T minus T is contained in U, and so that the mass of T tilde of T is less or equal to the mass of T plus delta. We have that the mass of T tilde of 1 is greater than or equal to the mass of T minus epsilon. So let me explain that. So the idea is that if you have, so this is my open set U, and maybe I have a varifold V like that. So this varifold V is going to be almost minimizing in U if one can find, if given some epsilon, I can find some T. T is very close to V in the varifold distance, so maybe T is like this. Maybe T is like that. So inside U, T is very close to V in varifold distance. The boundary of T is sitting outside U. And the property is that if I want to deform my chain T so that the area decreases by epsilon, maybe I can do that. But in order to do that, I have to pay a price of first increasing the area by delta. Okay, so what I'm saying here is that if I have a deformation, maybe everything is happening inside U. So if I try to deform my T so that the area decreases by epsilon, then sometime before in my deformation, I have to increase the area by more than delta. Okay, so maybe I can decrease the area, but in order to decrease the area, I have to pay a price. So that's what almost minimizing means. And so what Pitts proves is that, okay, so another definition related to this is that a varifold V in Vn of M is called Z2 almost minimizing. In annuli, if for every point P in the manifold, one can find some radius R such that for every radii, say S1 less than S2 less than R, I have that V is Z2 almost minimizing. In the annulus, say in M, let me note by this is the annulus, which is M intersected with the ball of radius S2 minus the ball of radius S1. Okay, so it's Z2 almost minimizing in annulus. If for every point P, I can find some radius, so that for every annulus contained in that ball, it's going to be Z2 almost minimizing in that annulus. And the point is that Pitts was able to prove this is called Pitts combinatorial theorem or argument. Says that if you give me a sequence of sweep outs, so say phi I, the sequence of sweep outs. So if I look at the critical set and if I have the property that no element, if no V in the critical set of phi I is Z2 almost minimizing in annuli, then one can deform the sweep out so that the area goes down. Okay, so then there's going to be a new sequence phi I prime. So the phi I prime is homotopic to phi I relative to 0, 1. I'm talking about one parameter sweep outs here, such that if I take the sup of the masses of phi I prime of t goes from 0, 1, then the lim sup of that as I goes to infinity is strictly less than the lim sup of the original sequence. Phi I of t. Okay, so the idea is that you have your sequence of sweep outs, and then when you look at the elements in the critical set, remember these are the varifold limits of chains with maximum mass. So these are the candidates for being minimal hypersurfaces. So if no such guy has the property of being almost minimized in an annuli, notice that if you say that a guy is not almost minimizing in U, basically this is saying that such deformations will be possible, so that you'll be able to decrease the area by a little bit and increasing very little in the mass. So I can't really go into the proof, but the idea is that if every such guy admits such deformations, then there's a way of pasting all those deformations along the interval 0, 1 so that you get a new sequence and the area goes down strictly. So the conclusion is that if your sequence happen to be a minimizing sequence, so the conclusion is that if Vi is a minimizing sequence, then I can't do that, right? The area cannot go down strictly. So that means that I can find some element in the critical set that does have the property of being almost minimizing. Okay, then there exists a varifold in the critical set such that is Z2 almost minimizing in annuli and because we had this pool-type argument, we can also assume have that V is stationary in M. So this is the effect of Pitt's combinatorial argument. And then regularity, which actually was done by Shen-Simon in 81. Let me restrict to the case where the dimension of the ambient space is in between 3 and 7. We'll say that if I have a varifold V in Vn of M that is stationary and is Z2 almost minimizing in annuli, then this guy is going to be smooth. So the actual statement is that there's going to be a disjoint collection, a finite disjoint collection, say sigma 1, sigma Q of smooth, closed, embedded, minimal hypersurfaces, and also integers M1, MQ, positive integers, so that my varifold V is actually just the sum of the minimal surfaces with this integer multiplicities. Okay, so it's really an embedded surface because the components are mutually disjoint. Each of them is embedded, but they could come with some integer multiplicity. Okay, because when you take the limit as varifolds, it could happen that maybe your surfaces develop some kind of neck, and maybe in this example here they would be converging as varifolds to this guy with multiplicity 2. Okay, so this is the regularity statement. In particular, this finishes the proof of Almgren-Pitt's theorem. For every compact Riemannian manifold, there's always at least one smooth minimal hypersurface. Okay? All right. So later I'll mention one conjecture that we have about this. So this is the regularity part. So are there any questions about this? Of course, in high dimensions, this hypersurface can be singular, but the singular set is relatively small, has codimension 7. Another remark is that if I said the dimension here the ambient dimension is at least 3. So if the ambient dimension is equal to 2, in the case of surfaces, then actually this is not true. For this theory at least, the Minimax object is actually a stationary graph. So not necessarily a closed geodesic. Okay, so the reason being that if one has maybe some stationary graph, there could be some point singularities, there could be some junctions, but those are fine because you only care about the almost minimization property in annuli. So you can omit these points, and this is perfectly almost minimizing in the annulus centered at that point. But if I take an intersection of planes, then given a point here in the intersection line, if you give me a ball here, well, I'm deleting the origin, but I still have an intersection point there, so you can decrease the area. So this is not almost minimizing in annuli. But this guy is. Okay. So if you want to construct closed geodesics, it's better to stick to the previous theory where we were talking about maps. Right? The point of the annuli? The point of the annuli is that it gives you many as many deformations as you want, because saying that you are not almost minimizing an annuli is equivalent to say that there is a point in the manifold such that no matter what the radius is, I can always find an annulus where I can decrease the area, and then maybe if you give me a smaller radius, I can find another annulus where I can also decrease the area here. So basically you can have as many annuli as you want where you can decrease the area. In order for this combinatorial argument to work, you need to have sufficiently many annuli to be able to paste these deformations. Okay, so actually this is true also for higher parameter families. The same argument. It's more complicated, but also works for higher parameter families. Okay, so this finishes the proof of one. So I guess the natural question now is, are there any other minimal hypersurfaces? So this is the question that we are interested in. Okay, so in order to answer this question, we really need to use the RP infinity structure. So our space of cycles is an RP infinity. So there's a weak homotopy between the two. So the homotop groups are the same. So in particular, you have RPK here for every k. So one thing you can do is you choose some family here parameterized by RPK. You can consider the homotopy class. You can do your minimax, right? Hope that will give you a different minimal surface. But of course, this is not really true because you could be getting the previous surface maybe with a different multiplicity. That's the difficulty. But actually, for the theory, for the Viol law that I'm going to prove and for other reasons, it's convenient to allow a general parameter space instead of fixing RPK. It's convenient to make the definition a little bit more flexible. And the right way of doing this somehow is inspired by Lussmann-Schneermann theory, is to use instead of the homotop groups, you look at the cohomology. So the idea is that the cohomology groups of this space are going to be the same cohomology groups of RP infinity. And turns out that H1 of RP infinity with Z2 coefficients is actually Z2. So it's generated by some cohomology class lambda bar. And then if I want HK of RP infinity with coefficients in Z2, this is also Z2. And it's actually generated by the product of lambda bar with itself k times. So it's going to be lambda bar to the k here. Okay, so lambda bar to the k is just lambda bar k times, where this guy is the product. So the same thing is going to be true for the space of cycles. So the same thing is going to be true. Therefore, I will use the same notation, so I will call lambda bar the generator of H1, the space of cycles, with Z2 coefficients. This is Z2. Okay, so lambda bar is just the non-trivial cohomology class. And it actually has a geometric meaning. So maybe it sounds a bit abstract, but it has a geometric meaning. So it's the following. So this is a cohomology class of degree 1. So I can evaluate the class in loops inside my space. So if you give me a loop S1 into the space, this is a one parameter family of hypersurfaces. And then remember that this family is going to be a sweep out if, when you keep track of the region this guy is bound, I generate the whole manifold. So it can either be homotopically trivial or not. And what lambda bar does is that lambda bar evaluated at sigma is going to return 1 if sigma is a sweep out. Being a sweep out means that it's homotopically non-trivial. And then it's going to return 0 otherwise. Okay, so lambda bar, I call lambda bar the fundamental cohomology class. So it's really the class that detects sweep outs. Okay. So then to make the following definition, I guess I can erase that too. So so the definition is that X is going to be an arbitrary, say, finite dimensional simplicial complex. It's not really fixed, it could be anything. And then you'd say that a map phi from X to the space of cycles. So X is really my parameter space. You say that a map phi is a k sweep out. I'm assuming that it's continuous in the flat topology. If when I consider the pullback of lambda bar under phi, I call it lambda. So this is an element of H1 of the parameter space with coefficients in Z2. The requirement is that lambda satisfies the property that lambda to the power k, which is just lambda coproduct with itself k times. I require that this is non-zero in the k-dimensional cohomology group of X. So that's the definition. Technically, I also need the condition that phi does not concentrate mass. Does not concentrate mass, but let's not worry about this. So an example is of a case sweep out is if you consider the map phi hat that I defined last time going from RP infinity to the space of cycles. Then the example is that if I restrict phi hat to RPK, this is a case sweep out. Okay, it's really a non-empty definition. So this is a case sweep out, but there are many more as long as you check this condition. Okay, so once one has a natural class of sweep outs, we can do minimax, and then actually I can define the following number. So I'd like to do minmax. So my definition is the following. So I say that the k width of some compact Riemannian manifold, the k width of some compact Riemannian manifold is defined by, is the number omega k of mg. This is the Minimax number. So let's say if phi is a case sweep out, let's denote phi belongs to, let's see, I guess I used a similar, I use pk for polyhedral chains, so let's use it again for different meaning here. So the minimax is for every k sweep out phi. Maybe I would just write phi is a k sweep out. So I don't need to do that. So for every k sweep out phi, I maximize the area, which is the mass, for every point in the domain of phi. And notice that the domain of phi might depend on phi. Okay, so that's the flexibility that I need, and it's going to be clear why this is important in one of the arguments that I will explain today. So for every k sweep out, you can maximize the area, and then you minimize over all k sweep outs. This is omega k of mg. It's going to be important in one of the proofs that I will explain here. Yeah, it's related to Lucent-Schnirman theory. Okay, so this is the domain of phi. X belonging to the domain of phi, so which might depend on phi. Okay, so this is the number. A metric invariant of the manifold. Okay. So some observations first, that if phi is a k sweep out, and if phi prime is homotopic to phi, then phi prime is also a k sweep out, as long as it does not concentrate mass. And also, if phi is a k sweep out, then phi is also a j sweep out for every j less than or equal to k, just follows from the power. And once I have my Minimax invariance, well, definition, I say that the volume spectrum of Mg is really the sequence. The sequence of numbers omega 1 Mg, and then because of the fact that a k sweep out is also a j sweep out for every j less than k, this is actually an increasing sequence of numbers. There might be some equalities here, but it's strictly, well, it's non-decreasing sequence of numbers. Okay, so RPK is not good enough. You can define these numbers for RPK. Yeah. No. Yeah. Not good enough. In the proof of, I'm gonna talk about this Viol law. In the proof of Viol law, it's important to have the flexibility of changing the domain. So sorry? Yeah. Well, because for some of the arguments that I'm going to explain here, I mean, I need to have, I need to use the cohomological definition. If you fix RPK, then you're talking about a homotopy class. But it's going to be clear in one argument that I will explain here why we need to allow this sort of thing. So actually, yeah, at this point I should say that the omega k is a minimax over a family that is not given by a homotop class, right? It's something more general than that. For homotop classes, one can do the same arguments as before. So I can do Minimax for a homotop class. I mean, the idea is the same, sort of like the same as before. For the one parameter case, you have, say, maybe pi, say, is the homotop class of some function phi. Now x is fixed. You fix some phi, then you look at the homotop class. Then one can define the minimax number L of pi. So this is Minimax. So for every family phi prime in pi, I can maximize again the mass, can minimize over all such maps, and then the Almgren-Pitts Minimax theory will imply that L of pi, the Minimax number, is always the area of some minimal surface. Okay, so it's going to be always of the, like as before, it's going to have the following form: M1 volume of sigma 1 plus MQ volume of sigma Q, where the sigma i's and the mi's are as before. So the sigma i's forms a disjoint collection of minimal surfaces, and the mi's are integers. Okay, so that's what the Minimax theory tells you. But they didn't really study the problem of the Morse index. Okay, in traditional Morse theory, you'd like to have information about the Morse index of the minimal surfaces. And some years ago, I proved with Andre index estimates. I proved following theorem with Andre in 2015, I think, that in this statement here, we can choose the sigma i's so that the sum of the indices I going from 1 to q is at most the number of parameters, which in this case is a dimension of x. This is the number of parameters. Okay, so this is really natural from the point of view of finite dimensional Morse theory. You should expect always that the index of the critical point matches the number of parameters, just like in the first example where we detected that critical point x1 by doing minimax over one parameter sweep outs. Okay. And actually, this index estimates turned out to be important, useful, in order to check that not only the homotopic minimax is achieved as the area of some minimal surface, but also the cohomological minimax number is also achieved. So the one corollary, which I'm not going to prove, but the corollary is so theorem that for each k natural number, there exists sigma I mi as before, such that omega k of mg is the sum of the areas with multiplicities. So the proof here, just say that it uses the index estimates plus a compactness theorem of Ben Sharp. So this compactness theorem is a compactness theorem for a sequence of minimal surfaces that have both the volume and the index uniformly bounded from above. Okay. So one can prove this. So every omega k is actually the area of some minimal surface. Well, one important conjecture that we make, we call it the multiplicity one conjecture, which is open, is that we conjecture that for a generic metric, this multiplicity should be all equal to 1. Okay, so it turns out that in mean curvature flow there is also multiplicity 1 conjecture. This is it could be kind of related, so it'd be interesting to relate the two. It's also open in that setting. So for the minimax setting, we basically conjecture that this multiplicity should be 1 generically. Okay. We can prove this in some special cases. All right, so the thing is that these numbers, omega k, they actually grow. So the first, I guess Gromov was the first person to study these numbers from a different point of view. He was not, yeah. Yeah, yeah. So sorry, what's the? Yeah. Yes. No. Here in the proof of this, I mean, omega k is not necessarily given by one homotop class, but it's actually a limit of numbers of that type. So it's a limit of homotopic minimax. So since each homotopic minimax is given by some minimal surface, and we can estimate the index of those surfaces, we can use this compactness theorem to take a limit. Okay, so it's actually a consequence of that by together with this two. I don't understand what you mean by the. I mean, this is a sequence of numbers. I'm just saying that each number is achieved as the area of some minimal surface. Okay, so what is easy to see is that omega k, each omega k is actually a limit of numbers of that type. Okay. No. This is just. I mean, this is just a number, right? I mean, I'm not. I'm just saying that there are these minimal surfaces such that this is true. So it's an existence result. Okay. So, I mean, these surfaces are not defined canonically. I'm saying that there exist some surfaces such that this equality is true. Okay. So the Gromov-Guth bounds. So they prove that actually these numbers grow to plus infinity, and they grow with some order. The interesting thing is that the order is actually sublinear in K. So they prove that there exists some constants. So Gromov gave the first proof, then Guth reproved it in a nice way. So there are positive constants depending on M. Such that omega k of mg satisfies this thing. Okay, so they grow with the 1 over n plus 1 power of k. I won't prove this, but because I'd like to prove the Viol law, which is related. So let me say that we were actually a few years ago, well, 2013. I wrote a paper with Andre where we use the sublinear growth to prove the following theorem. So we proved that for a general, not generic, for a general manifold M of dimension n plus 1, I have two possibilities, which are not mutually exclusive. But possibility A is that there exists a disjoint collection say sigma 1, sigma n plus 1 of n plus 1 minimal hypersurfaces. So I should say here that either I can find a collection of n plus 1, a disjoint collection of n plus 1 minimal hypersurfaces, or there are infinitely many. Or there are infinitely many minimal hypersurfaces. So the corollary of this is that first, maybe I shouldn't say corollary, but some remarks here that n plus 1, so the corollary is that there's always at least n plus 1 minimal surfaces, right? Because either in A or B, I get at least n plus 1. So there's always at least n plus 1 minimal hypersurfaces. And for general matrix, this is the best result so far. No, Almgren-Pitts proved that there is at least 1. We can improve that to n plus 1. And the second consequence is that if the Ricci curvature is positive, this particular case, possibility A cannot happen because there's a theorem of Frankel that says that in positive Ricci curvature, two minimal surfaces have to intersect. So it cannot be a disjoint collection. So because of that, if Ricci curvature is positive, actually there are infinitely many minimal hypersurfaces. So the situation that we cannot rule out, although we believe that it cannot happen, situation cannot rule out, is the possibility that there could be a disjoint family of n plus 1 minimal surfaces such that every omega k is a linear combination of areas of this collection. Okay, so that omega k is maybe some number m1k sigma 1 plus m n plus 1k sigma n plus 1, where these guys are integers. In other words, I can do minimax for k sweep outs and I can get a minimal surface, and these numbers grow, but maybe I can generate all these numbers by using only n plus 1 minimal hypersurfaces. Okay, so this is a situation that is still we cannot rule out. Of course, yeah, as I said, generically we expect the multiplicities to be equal to 1, but in general, multiplicity can happen. All right, so let's see, I'm gonna check my time. Okay, so now I can talk about the Viol law, which is really the main tool in the proof of the denseness and equidistribution. Maybe I should mention an example here that one remark is that this number, omega k of mg, for a particular manifold mg, is actually very difficult to compute. So let me describe one example. So if my manifold is the round 3-sphere, the unit 3-sphere, then remember that I had this map from Rp, in this case is Rp4, to the space of cycles here, 2 cycles in S3. This is the map that gives me, if it gives me a point A0, A1, A2, A3, A4, I associate the round sphere given by the set of points in S3 such that A0 plus A1 x1 plus so on A4 x4 is equal to 0. So it gives me, I'm parametrizing the space of round spheres by Rp4. So one can check that this is a full sweep out. And of course, the area of a round sphere is at most 4 pi. So this implies that the first 4 widths of the round S3 are at most 4 pi. But they're also at least for pi, because for pi is the lowest area of a minimal surface in the round S3. So I can compute omega 1 of round sphere throughout omega 4. They're all equal to 4 pi. And actually, one can also compute omega 5 of S3G bar. This turns out to be 2 pi square, the area of the Clifford torus. So this is somehow related to the Wilmot conjecture. So we do not know much more than this. I mean, this is going to be 2 pi square for maybe until omega 9 or something, and then we don't know what the next one is. Okay, so it's different from the standard spectrum that in some particular cases you can compute them all. Here, you cannot really classify minimal surfaces, so it's very hard to compute exactly these numbers. Anyway, the traditional Viol law, let me just recall it very briefly here. So the Viol law 1911 says that if I have a compact Riemannian manifold, I have the standard spectrum given by the eigenvalues of the Laplacian, and then the Viol law says that if I take the limit of these eigenvalues normalized by like this, so there's equivalent ways of writing this, but this actually recovers the volume of the manifold. So there exists some constant positive which depends only on the dimension, such that the limit of this is always this constant, and then the volume of AMG to the power minus 2 over n plus 1, where this guy is the lambda 1, lambda 2, and so on. This guy is the spectrum of the Laplacian. So Gromov conjectured. So Gromov wrote, well, a couple of papers on that. The first paper was actually a 1988 paper, where he talks about Viol laws. He talks about the relation between the standard spectrum and this spectrum. He also wrote a more recent paper where he explicitly conjectures that the volume spectrum obeys a Viol law. So that's what we proved. This is joint work with Leo Kumovich and Andre, 2016, that the conjecture is true. So there exists some dimensional constant A of n positive, such that if I take the limit as k goes to infinity of the k width normalized, so I multiply it by, say I divide this by k to the power 1 over n plus 1, this converges to this dimensional constant times the volume of m to the power n over n plus 1. So this is the Viol law for the volume spectrum. One difference between these two Viol laws is that here one can compute the constant, because as I said, in standard examples one can compute all the eigenfunctions and then you can compute the constant C of n. Here we cannot compute. It's an open question what the constant is, because one cannot classify minimal surfaces. But it's still, I mean, the point of this is that you get the same constant for all Riemannian manifolds. So this is what I call the Viol law. Well, it's a Viol law for the volume spectrum. So I'd like to finish the mini course giving some idea on how to prove this. So are there any questions at this point? Oh yeah, yeah. Yeah, of course, from the bounds by Gromov and Guth here, we know that the ratio is bounded between two constants which depend on the manifold M, right? But the point is that they're actually converging to something that is universal. Okay. So, okay, so the normalized, I'm going to sometimes use the normalized with, and this is the number omega k tilde, which is just going to be omega k divided by k to 1 over n plus 1. Anyway, the main ingredient in the proof of the Viol law is what we call the Luster-Schneermann inequality. So we call this the Luster-Schneermann. Inequality. By the way, one important observation is that the Viol law actually makes sense also for manifolds with boundary. So let me point this out here. So for a manifold with boundary, so if the boundary of M is non-empty, so something like this, maybe this is the boundary of M, one can still talk about cycles, but they will be relative cycles. So T, like in this picture here, is a relative cycle, which means that the boundary of T is contained in the boundary of M, and of course you ignore everything that is contained in the boundary of M. So the space of relative cycles is denoted in this way. And it's still true that, because I can talk about relative chains, the same structure holds true here. This is also an RP infinity guy. Okay, so actually the Viol law is for manifolds, possibly with boundary too. It's important for the proof. So the inequality says the following. Suppose that you have some manifold with boundary omega 0, and then inside omega 0 you have a bunch of disjoint regions, say omega 1 to omega p. So this is, they are contained in omega, and they are omega 0, and they are mutually disjoint. Then the inequality says that omega k of the big region is greater than or equal to the sum of the omega ki's of the smaller regions, provided the sum of the ki's is less than or equal to k. Okay, so this is the inequality. So let me prove that for you. So it's interesting that this is where we use the cup product structure, and the fact that the domain is allowed to vary. So the proof goes as follows. I'm going to consider a k-sweep out of the big guy. So instead of thinking of a map, I would think of a k-sweep out as really a family of hypersurfaces for simplicity. So think of S as being some family in the space of relative cycles of the big guy. And suppose this is a k-sweep out, which basically means that if I look at my cohomology class here, the fundamental cohomology class, lambda bar, then lambda bar to the power k restricted to S is non-zero. That's the condition of being a k-sweep out. Okay, so now consider the intersection map. So if you give me, say, a relative cycle in the big guy, say maybe T, of course I can intersect it with the smaller region. I get a relative cycle of the smaller region, right? So if I consider the map that takes, if T is a relative cycle of the big guy, and then I just intersect with the I region. Now this is a relative cycle of the smaller guy. So the observation is that this map preserves lambda bar. So of course, for each, if I'm talking about relative cycles of the smaller guy, I have some cohomology class there, right? So why is this true? Well, it's true because remember that the fundamental cohomology class is the cohomology class that detects the sweep outs. So if you give me a sweep out, if you give me a family of hypersurfaces of the big guy, it's going to be a sweep out if it spans the whole thing. So given a family of the big guy, if it spans the whole thing, then the intersection with the smaller guys also is going to span the whole thing here. Okay, so a sweep out of the big guy by intersection corresponds to a sweep out of the small guy. So this map actually preserves the fundamental cohomology class. So now inside S, I consider the subfamily Si, which is going to be the family of cycles in S, such that the mass of the intersection with omega I is not big enough. So this is smaller than omega Ki of omega I. Okay. So notice that when I do this, if S happen to be some projective space RPK, now I'm changing the domain, you see? The Si doesn't have to be a projective space anymore. So that's why we need this flexibility. So I look at this guy Si. So these are cycles such that when I intersect, I'm below the omega Ki number. And because this intersection preserves the class, the implication is that if I take lambda bar to the power Ki restricted to this subfamily, this is going to be 0, right? Because I'm below the optimal number for that power. So this power has to be 0 in the subfamily. And then it's the basic fact about curve product is that this will imply that if I take K1 plus Kp on the union S1 SP, this is going to be 0. This is the only thing we need to know about curve products. And of course, the sum of the Ki's is assumed to be smaller than K, so lambda bar to the power K also vanishes in this union. But we were assuming that the original family S detects that power, so the conclusion is that there must be some cycle sigma which belongs to the original guy and is not in the union. That's one. But then, if this is true, the mass of that cycle, of course, this is bigger than the sum of the masses of the intersections. But now, because sigma is not in the subfamily Si, the mass of the intersection has to be bigger than this number. And this finishes the proof. So what I showed is if you give me a K-sweep out of the big guy, I can always find a cycle in that family whose mass is bounded from below by this number. So you get this inequality. Okay. So this is the Lussner-Schneermann inequality. So the Lussner-Schneermann inequality actually implies the Viol law for the cube. Let me do that. See how much time I have. Still have time. I go until 5, right? Yeah. So are there questions about this argument? So now take C to be the unit cube in Rn plus 1. So it's just a cube. Okay. So the lemma that follows from the Lussner-Schneermann inequality is that if I take the normalized k widths of the cube, the lim inf of that as k goes to infinity is equal to the lim sup. Okay, so we're going to prove the Viol law in steps. The first step is to prove it for the cube. So this is saying that these numbers actually have a limit. So the proof goes as follows. Let's choose some subsequences, say maybe PL and QJ contained in the natural numbers, so that if I take the limit of omega PL tilde of C, this goes to the lim sup. And say that the limit of omega tilde Qj of C goes to the lim inf. I want to prove that these two numbers are the same. Okay, so choose subsequences like this. So now you fix L. Let me erase this. Fix L. And let's take J sufficiently large. So take J sufficiently large so that the ratio between PL and QJ is less than 1. Let's call it delta J. So now what I do is I look at that number delta J that is smaller than 1. Actually, this is going to 0. And I'm going to choose the maximum number of cubes that I can. I'm going to try to pack these guys. So Nj is going to be the maximum number of cubes. Say Ci star of volume equal to delta J inside C. Okay, so delta J is the small volume. I try to put as many cubes as I can with that volume inside C. Then it's clear that as the cubes become very, very small, the total volume that I can cover converges to the whole thing, to 1. So I have that Nj, this is the number of cubes, times the volume of the cubes, converges to 1 as J goes to infinity. Now I will use the Lucent-Schneerman inequality for this situation. I have the whole cube C is going to be omega 0, and the smaller cubes Ci star are going to be my subdomains. So the Lucent-Schneerman inequality that we proved implies that if I take the omega, let's say Qj of the big guy is bigger than the sum I going from 1 to Nj. This is the number of small cubes of omega Pj of Ci star. Okay, so this is because, the condition that I need to check is this. So if I take the number of cubes is Nj, if I multiply Nj by Pj, sorry, this would be, I changed here, so this would be Qj, this is PL. Yeah, Nj times PL. So Nj times PL, as you can see here, is basically Nj delta J Qj, and of course Nj times delta J converges to 1, but converges from below, right? Because the volume is smaller than the volume that I cover is smaller than 1. So really this is smaller than Qj. So I'm in the conditions of the inequality. So I get this. But then Ci star is just a scaling of the big cube, right? So and this is supposed to be an n-dimensional area. So it scales like n-dimensional area. So I can relate this to the omega PL of the big cube. I get omega PL of the big cube, and then I get the scale, which is delta J. Delta J is an n plus 1 dimensional volume, so there is a power here of n divided by n plus 1. This is just a scaling. So that's what I have. Of course, these numbers are all equal to each other, so this gives me omega PL of C times nj delta J to this power. So let me erase this. So this is an inequality that I have. I want to look at the normalized width. So if I normalize things, I will get that I have to divide the left-hand side by Qj to this power. This is greater than or equal to, I'll have this factor here, times nj delta j, and then omega PL of C, and then we just need to finish the calculation. So I think I can write this as nj delta j minus 1, and then I have this guy. Then I have that guy. So this number here is converging to 1. And then, of course, I want to also normalize this. So I put PL minus 1 over n plus 1, then PL 1 over n plus 1. So now you just remember that PL divided by Qj is equal to delta J. Right? So I get here this thing. Here I get delta J to the power minus 1 over n plus 1. And then from these two guys, I get delta J to power 1 over n plus 1. And then I have the normalized width of C. Of course, these guys cancel. This is converging to 1. So if I take the limit as j goes to infinity, because this is converging to the lim inf, I conclude that the lim inf of omega tilde k of C is greater than or equal to omega tilde PL of C for every L, because I fixed L from the beginning. Now you take the limit as L goes to infinity, this converges to the lim sup, and then we are done. And get at the lim inf is greater than or equal to the lim sup. Okay, so this proves the Viol law for the cube. So now the next step is to prove the Viol law for domains in Rn. So here are the steps. So this was the first step, prove it for the cube. So the second step is to prove that if you give me a domain in Rn plus 1 actually, I can prove that the lim inf of omega k tilde of this guy is going to be greater than or equal to A of n. By the way, this is my definition of A of n, okay? So the volume of the cube is equal to 1. So because these two numbers are equal, I define this number to be my A of n. Okay, this is my dimensional constant. So in order to prove this, you just need to, it's also a packing argument. So you need to pack omega with little cubes, small cubes. And because you know the result for the cube, you get this. Third step, you prove that the lim sup of omega k tilde of this guy is less or equal to A of n. And the argument here is you pack the cube with scaled copies of omega. And you do a similar thing. So this proves the Viol law for domains in Euclidean space. Arbitrary domains, yeah. So number 4, now I want to consider the case of Riemannian manifold. So number 4 is actually one can prove that the lim inf of omega k tilde of a Riemannian manifold is greater than or equal to A of n. And here what you do is you pack your Riemannian manifold with small geodesic balls. And the idea, of course, is that a small geodesic ball is almost an Euclidean ball. And we already know the Viol law for Euclidean domains. But the final step, which is to prove that the lim sup of these numbers is bounded from above by A of n. This step requires a different argument. Why? Well, because I cannot pack a cube with Riemannian manifolds. Right? So I'd like to finish with the proof of 5 because it's an interesting argument. So here's the idea. Let's see, still have 10 minutes. So proof of 5. So you have some Riemannian manifold M. So I can triangulate my manifold. I choose a triangulation. So I can decompose M, the union of triangles, so that the triangulation is very fine. So the triangles are very, very small. In particular, each triangle lies in a region that is almost Euclidean. So given any epsilon, you give me an epsilon, I can find a triangulation so that each triangle is 1 plus epsilon by Lipschitz to some domain in Rn. Maybe I'll call the by Lipschitz homeomorphism Bi. So what I do is I have this region, these omega i's in Rn plus 1, which are by Lipschitz to the triangles with a constant that's close to 1. So what I can do is maybe I can translate them so that they are disjoint. I can add some tubes here with very small volume, and I can build an artificial domain in Rn plus 1. So this would be connected sum, omega 1 to omega n. So these tubes have very small volume. So I can do that so that this is my omega. The volume of this artificial domain is almost the volume of M. So it's actually the volume of M plus an error that is of the order of epsilon. Okay? So I have my artificial domain. So now the idea is that I want to estimate the k width of M from above. And I know how to do that for omega because I already know the Viol law for for domains in Euclidean space. So what I'm going to do is I'm going to choose a sweep out of omega that is almost optimal, a K sweep out that is almost optimal, and I'll try to transplant that sweep out to M. So you give me phi, a K sweep out. So it's a relative sweep out of omega. This is going to be a K sweep out. So this means that if I take the pullback, if lambda is the pullback of the fundamental cohomology class, I will have that lambda to the power k is non-zero in X. So this is the property. So I can choose phi to be almost optimal, okay? So maybe I can choose phi so that the sup of the masses is almost omega k of omega. So maybe plus an order which also depends on epsilon. Okay, so let me draw a picture. Maybe it's easy to explain with a picture. So a typical element here would do something like this. Maybe a component like that. So maybe goes into the tube, I don't know. So this would be a guy like this, phi of X. Okay. So what would be the naive thing to do? So the naive thing to do, the first thing you would think of, although it's not going to work, is that I can consider the intersection. So say this is omega I. I can consider the intersection of this guy with the omega I region. And because I have a bi-Lipschitz homeomorphism with the triangle, I can use this homeomorphism to bring this guy to my manifold. So maybe I get something like this. And there's the same here. Well, the problem if you do that is that this is not going to be a cycle, okay? Because I'm losing information here. So this doesn't work. I mean, it's easy. It's nice because I can estimate the mass, but it's not going to be a cycle. So you think, okay, now this doesn't work. So instead of doing that, of transplanting the hypersurface, I can try to look at this region. So I can transplant the region, maybe here, and then I can compute the boundary of that region. So this is better. Because now I can do that for, no, maybe here I got these regions like that, so maybe they go here. Compute the boundary. Maybe there will be some cancellation here. But the thing that matters is that now the guy that I have here is a sum of boundaries. So if it's a sum of boundaries, it's a cycle. Okay, so this is good. But the problem is that I have two choices of region, and I don't know which one to choose, right? So we're going to solve that by a topological argument. So what you do is the following thing. If this is my, maybe this is my omega I, then I have, this is going to be my phi of X intersecting that omega I. So I'll call phi I of X the intersection. So it's really this thing here. So as I said, there are two possible regions. So how do I encode this? I'm going to denote by, let's see, SXI. The following thing. I consider the set of pairs X, Z, such that X is in the parameter space. Z is a region inside omega I, with the property that the boundary of Z is my guy, of course, modulo the boundary of omega I. So as you can see here, there is going to be two where's my color? Anyway, there's going to be two choices, right? This, maybe some x z1, and this maybe x z2. There are only two possibilities. So the projection, if I consider the projection from this guy to x, it takes xz and sends me x, is a 2 cover. And the point is that if you recall a little bit of topology here, a 2 cover is actually classified by a cohomology class of degree 1 on the base. It's called the first Stiefel-Whitney class. The idea is that if you give me a loop in the base, so this cohomology class evaluated at the loop is going to be 1 if the lift of the loop is open, and it's going to be 0 if the lift of the loop is closed. So that defines a cohomology class here. So a 2 cover is classified by that cohomology class. And it's easy to see that in that case, the cohomology class is going to be lambda for every I, the lambda that I had here. So a topological argument will imply that S, X, I are all isomorphic to each other. So I have an isomorphism, maybe say lambda I, which goes from Sx1 to Sxi. So the point is that in each omega I don't know which region to choose. Maybe I choose this region on the left, maybe I choose the one on the right. I don't know that, how to choose. But once you pick one, you have picked corresponding regions in all the other ones because of the isomorphism. So then, here's what you do. So I'm going to define a map, a psi hat, which is going to be defined in the first 2 cover, and it's going to take values in the relative cycles of my manifold M. So what I do is, if you give me a point here, so it's a point and some region Z, so I chose one in the first omega 1. So what I do is, now I look at the corresponding region in the omega I, so this is given by the isomorphism. So this is a pair, so this is a region in the other guy, so I look at the corresponding region, let me call it the Zi, the corresponding region. Then I transplant that region to my manifold using the homeomorphism, the bi-Lipschitz homeomorphism, I call that Bi. Notation is a bit heavy, but I hope that you get the idea. And once now I have a region in my manifold M, I can compute its boundary. And then I can sum that over all i's. 1 to n. Okay, so it's really the sum of boundaries. So what are the observations here? First is the sum of boundaries, so it's a relative cycle. The boundary is going to be 0. Modulo, of course, the boundary of M. But it is still not good because it's defined not on the original parameter space, but it's defined on Sx1, because I don't know how to choose a region. But the point is that suppose I switch the region Z to its complement. So if you look at psi hat of X and then its complement, what's going to happen is that if I switch the region in the first guy, I'm going to switch the region in all the others, right? So when you look at the picture here, I have my triangle, and then I had an original region like that, right? So if I switch the region and compare the boundaries, well, the inner boundary is going to cancel because it appears with multiplicity 2. So the sum is actually going to give me the boundary of the triangle. So when I switch the region and do all the sums here, I get the original guy. plus the sum of the boundaries of the triangles. Well, if I sum the boundaries of the triangles, maybe my manifold has boundary. Maybe here's the boundary. If I sum the boundaries of the triangles, of course, the inner faces are going to cancel because they appear with multiplicity 2. And I'm left with the faces that are contained in the boundary of M. So this is really the boundary of M. So what I have proven is that if I switch the region Z to its complement, I mean, this guy is really not the same, but as a relative cycle in M, they are. So they define the same guy, the same relative cycle in M. So the conclusion is that my map psi hat actually descends to a map psi on the base if I consider relative cycle. Well, now it's just an exercise to check that this guy is going to be a K-sweep out of M, because the cohomology class will be lambda, and lambda satisfies this property. And the remaining thing to do is to estimate the mass. But if you look at the mass of a typical element here, well, by construction, so maybe, let's say I get something like this. So if I try to estimate the mass of the guy in M, you see that there are two types of contributions. First, there are the inner part, right? The interior part. But the interior part is coming from phi of x in omega, right? So I can estimate the sum of the interior parts by the mass of phi of x, the original guy, well, times it's a bi-Lipschitz homeomorphism, so maybe there is here an error of order epsilon. So this is the contribution coming from the interior part. But I also have this part here contained in the boundary of the triangle. But because, you know, again, the multiplicity is at most 1, the second part is going to be at most the sum of the masses of the boundaries of the triangles. This is the estimate that one gets. And then, well, finally, what do we do? This already gives me that omega k of mg. This is less than or equal to the sup of the masses of psi. So I get this estimate. Again, the sup of the masses of phi, I chose so that this is almost omega k of omega. Maybe up to an error of order epsilon. Here I have the sum of the masses of the boundaries of the triangles. And finally, what I like to do is to divide everything by k to the 1 over n plus 1 power. So you divide here by k 1 over n plus 1. You divide here k 1 over n plus 1. Divide here by k over n plus 1. And then when you take the limit as k goes to infinity, the lim sup of this guy, the normalized width, or if I choose my sweep outs of omega so that they satisfy the Viol law, this gives me 1 plus order of epsilon. This gives me the Viol law term for omega, which is a of n, then the volume of omega. And now this thing vanishes, right? Because I have a fixed number here, k's go to infinity, so this goes to 0. So then you just have to remember that the volume of omega is the volume of m plus something of order epsilon. Then when epsilon goes to 0, you get the result. A of n, volume of m. Okay, so there actually, I could have mentioned some questions here. For instance, one question that the traditional Viol law has always a remainder term. One can ask whether there's a remainder for the traditional Viol law. But the point is that this formulation is already enough to get the conclusions about denseness and equidistribution. And I'm going to talk about that in my lecture on Thursday. Okay, so I end here. Thank you. Thanks. Yes, Paul. A3, yeah, that's a good question. It would be very nice to have at least a sequence of minimal surfaces that are candidates to give you the number. Yeah, one can estimate the number, but in order to compute it explicitly, even for A2, we don't know what A2 is. You can take like families of given by zeros of polynomials that will give you some estimate, but yeah, it's an interesting question to see what constant is. Okay. Okay, thank you. Thanks.